Hello, my name is Bernard Rivera, and I want to welcome you to my video tutorial on writing shaders using OSL inside of Blender. Today I'm going to walk you through the basics of C-like syntax, or rather, how you actually write programs correctly using the C language, which is the basis for the syntax inside of OSL. And then I'm going to show you how you apply these basics to actually writing a shader. The shader we'll be writing today is this fractal-like pattern. This is the code, but of course, if I walk you through the code, you won't learn all that much. So what I'm going to do is show you first the basics of the syntax, and then we're going to build this code up together. I'm going to show you the process that I went through to make this code. So let's get started. I'm going to load a new blend file. I'm going to turn on screencast keys so you can see what I'm doing. So you want to delete everything here because we don't need it. And for some reason it doesn't want to delete. Next we're going to split the screen about like there. And then we're going to split it again, this time sideways. This will remain your 3D viewport. We're going to change this to a text editor, and this one to a node editor. Before we continue, make sure that you're using the Cycles render engine. If it doesn't show up here, you're going to want to go here in File, User Preferences, Add-ons, scroll down to Render, and it'll be the Cycles render engine. You click it on, and then you save your settings down there. Next, you want to make sure that your Open Shading Language support is available. So you have to click here. Next, we're going to add a mesh. It's going to be a plane. We're going to zoom in a little bit to see better. We want to grow it to double its size, so it's a little bit larger. And then we're going to get a top view on it. We're going to add a shader down here, or BSDF, whatever you want to call it. We're going to get rid of this diffuse. We don't need it. Then we're going to add a script here, which is going to be our OSL scripts. Then up here in our text editor, we're going to add a new text. So before we actually get started writing this shader, I'm going to explain to you the basic data types, and then some of the necessary structures that we need to be able to write programs. So the basic data types for most computer languages are, for example, an integer, which is an int, a float, which gives you real numbers, that is, numbers with fractional values, such as 10.5. An integer can't hold that, it can only hold whole numbers. Then you have string, which is symbolic, or symbols. So letters, numbers, and then the symbols that you can use, like shift clicking any of the numbers. And then you have also arrays. But OSL has some other types that aren't used in other languages because they're not necessary, such as the point-like types, the color types, and the closure types. I'll explain these all in due time. Let's start with the syntax for an integer. So, when you're declaring any sort of data type, you have to declare the type. So, to get a variable, you would say int, say you give it a name, so we could call it a, and then you can set that value equal to 5 because it's an integer. You could say it's equal to 5.56583, but when the compiler sees it, it will just chop off the decimal place. It won't round up. It always just cuts it off. So it could be 5.9999999. I missed the points. Oh, and I just did that. And the compiler will give it a value of 5. That's how it works. So there's a few ways that you can declare this variable. You can just say int a, and then you have this variable a. You don't know what the value is, because it's stored in your memory. It could have any value you don't know. And ints are not declared to be 0, so it will just have some random value. So usually it's useful to declare it and give it a value. I usually like to declare it to be 0, but if you know you're going to give it a specific value later on before you use it, it's not necessary. So you have inta. Let's say we have an intb, and we're going to give this a value of 8. Later we can say a equals 8. But there's some tricky stuff that it might be a little crazy when you first see it, because it doesn't really work out like math you think it would. You can say a equals a plus b. You're like, whoa, I learned in math class, if you have a equals a plus b, it's equal to 0 equals b, because you can take the a from both sides. But we know that b equals 8. So how does that work? Well, this equal value is not really an equals. What it does is it gives this data type the value of the right side. So what this actually says is find the value of a, which is 7, plus 8, and then plug that into a. So I hope that you understand that, because it's very important, usually when you want to increment the value by a certain amount. Now let's go into floats. Floats, it's the same thing. You have the type float, you give it a value of, we'll call it value. You can declare it and initialize it to a value. And it's the same thing, and the only difference is that floats can hold fractional values, so it can be equal to 7.2345 and such. Before I move on, I want you to be aware that, for example, when you do multiplication with using ints, say int a equals 9 and int b equals 8. You would say I want int c to equal 8 divided by 9. Because we know that integers can only have whole numbers, they chop off the decimal points. C actually ends up being 0 because, well, I meant to write it as a b. Ends up being 0 because this fractional value is equal to, I believe, 0.88888. So it's going to chop that off, and C is going to be 0. That's something you have to be very careful of, because it can give you some errors, and you'll be hitting your head against the wall trying to figure it out. And the error will be simply that semantic, that concept that integers, when they're divided by other integers, end up being, not having that fractional value. In fact, if you have a float type b equal to 4 divided by 5, this b will still end up being equal to 0, because since these are two integers, they will end up being 0 because the decimal part gets chopped off. So how do you get around this? Very simply, you can just say 4 divided by 5.0, because 5.0 is a float type. When you do this division, this will end up giving you a float value, and there this will actually end up being 0.8. Everybody's happy. Okay, so before I explain strings, I want to explain arrays. So if you've heard this word before, you know that it's like a conjunction of the same thing. So you can have an array of computers in your render farm. It'll be just computers that are lined up together in a group. So that's basically what arrays are in computer science, in programming languages. They are collections of one type. So interestingly enough, arrays aren't declared as type array. They're declared as the type of data you want to put in. For example, if you want to have a collection of float values, you would say float. Now, next we know that we need a name for this array, right? I'm going to call it values because I'm really clever at thinking of names. Then you do this square bracket, which we haven't seen before. This will give you a length of your array. So say you want 5 values, you put 5, close bracket, and then you put the semicolon. You should always end any statement with a semicolon, but we will talk about this later on. And now, why is this useful? Well, what you can do is you can actually access individual data types inside of this array. So you can say the value at index 0, which all arrays, or rather in C, arrays start at index 0, and the highest index you can have is your length minus 1, because again, it starts at 0, not 1. So values at index 0 is your first value. You can say equal to 1.2535. Then you can say values of index 1 is 2.65. Again, I must reiterate that I'm really clever at thinking of things while I'm typing them. So we're going to say values of 2 is going to be values of 0 plus values of 1. So here, again, the index of 2 of this array values is going to get the value of that array at index 0 plus the value of that array at index 1. So the first and second values are going to add together, and they'll become the third value. That's basically it. Next the next type is type string. It is actually an array of characters, and you can access it as such. So your type is going to be string. I'm going to call it word, and I'm going to set that equal to hello. So something we haven't seen before is using these quotation marks. They're necessary for when you're using this type of string. It tells the compiler, hey, this is a collection of characters, and you have to do it or else you'll get an error. So generally you can actually access word, and you can say word of 0 equals, say, actually not 0, make it word of 1. So the second character in the word, we're going to set it equal to a. And then you get hallo instead of hello. You know how German people say it. I don't know why they say it like that. I guess that's how it started. But that's a whole different topic. So we've finished the basic data types. Now we have to go on to these other data types that OSL has that don't really exist in other languages because they're not needed. These are the points. I cannot type today. The point-like data types, which is point. Point is point-like because it is a point. Then you have your generic vector, and then you have your normal. Under the hood, all of these three types are exactly the same. They will hold 3 float values because they're vectors in 3 dimensions. And the way you construct them is pretty much the same. However, it makes for a better style to use points only when you're using points being shaded. vector for just a vector in your 3D space, and normal for your shading normal. It makes it more readable. It makes it easier for people to understand where you're coming from and why you're doing certain things in your code. So, again, when you declare something, you have to give it a type. Type is going to be point for now, and we'll call it position. And say you want to get the position of the point in that you're being shaded in the space of your scene. Well, there's a global variable, capital P, which gives you that position. It's equivalent to plugging in, say, your geometry node and plugging in position. It's the same exact thing. Either way, it does the same thing. But if you can put it inside your shader, it makes for a smaller shader tree. It makes it easier to follow. Same with, for example, normal, I'm going to call it norm equals n. This is the shading normal of whatever position is being shaded at the moment. An interesting thing about OSL is that because it's not really a program as much as like a plugin, you don't actually have to state the position that you're at and shading that. It does it automatically. Where normally you would have to use like a loop to go through every single point. The compiler does it automatically, so you don't have to worry about that. And vector, finally, it works the same exact way. Vector vec equals, and you can give a specific value that you want, say 0, 1, 2. Now you can do this for normal and for points, but generally you would be using those types for a value that you're given in your scene, so you wouldn't really want to give it its own specific made up value. Again, this is actually a type of array, just like string, so you can actually access individual components of it. So vec 0 would be equal to 0 if you were to call it, and just like that you can make vec 0 equal to vec of 2. And this is going to be useful in the shader we're going to make. One thing that you should keep in mind is that when you're using these point-like type values, your first value is going to be your x value, your second value will be your y, and your final value will be your z. Now moving on to the type color. I'm going to give it a name color. So we have the data type, the name of it. It's fine that it's the same exact word as long as we capitalize the C, because then it's a completely separate word to the compiler. And the way you would do this, to declare color, you could say this color equals 0.5. What this does is gives the RGB values all value of 0.5. You can also do it by color equals, you do this constructor color, and you say 0.3, 0.4, 0.5. And it gives the R, the red value, 0.3, the green value of 0.4, and the blue value of 0.5. And then finally there's another special thing you can do using the same constructor color, which a constructor basically does, it builds you an object of this type, so it builds you this color. And instead of doing just how we had before, we're going to give it a string as the first parameter of the constructor, so we can say HSV, and then we're actually making a color in HSV color space, which HSV stands for hue, saturation, value. So here you can give it a value of 1, so the color is completely saturated. I'm sorry, this is the hue 1 is actually red, then the saturation will be 1, and then you can have the value also be 1. So this is like a very intense red. And what you could do is if you had a variable that calculates something, you can actually plug in the variable, for example, variable I, into one of these, and it'll build you your color depending on the value of I, which is very useful for doing pattern, generating patterns. That's all for the data types. Oh, sorry, I almost forgot the last one, closure. Now this is, I don't really consider it a data type as much as it's basically just a shader. So your closure is actually made up of your closures, that is your shaders. I'm going to open it up over here, different shaders we have. Because I believe in OSL we have all these shaders that are available to us in just the general interface for cycles. And there are some extra ones that aren't yet available outside of OSL that we can use. But we're not going to worry about that for now. If you want to find out about different types, you can go to the, I'll put a link in the description. Blender actually has a repository of the different nodes that can be used in Blender as OSL shaders. In this repository, they also have all the closures and all the necessary parameters you need for them. So I'll put a description there. I'll also put a description in the description. I'll put the link to the OSL spec sheet so you can get reading it if you want, and it'll give you a much deeper look into the language so you can do more advanced things. So, so closures actually closure colors, which is kind of weird. You think it'd just be closure, but that's okay, closure color. So you give it a type, and then you have the name, you can call it VS, DF. And you can set that equal to 0 if you want. And then later we'll show you how to actually give it a shader, or make that closure color equal to one of the shaders that are built into Blender. Finally, I want to get into this concept of a struct, which we won't be using in this video, but it can be very useful for combining different data types into one. So say you want an array, and you want, for example, the name of this your float to be a string, and you want to be able to say, hey, if this string is this string, I want you to give me that value. Well, unfortunately, you can't just have an array and have different data types inside the array, because all arrays, you declare for the array, you always declare, for example, the type float. And you have, array, and then you have a length. You can only plug in floats. So the way to get around this is using what's known as struct. Struct. Like it's like this. It's not even a data type. It's like this object you can put data types into. So the way you declare struct, you do this at the top of your code. You say struct. You give it a name, such as complex. You do open brace. You can say float real, and then float image for imaginary, which if you like math, you understand that a complex number is made up of a real and imaginary component. And this is the way you would go about making this complex thing, so you can always remember that, hey, I have this value, a type complex, and it has two different components, and you can access these and set them separately, like so. So you have the struct already declared up there, so you call it, it's a type complex, because that's the name you gave it. You can call it position, so it's declared, then you can use position dot and then you say real. So what it's saying is, hey, I have this complex data type that's called position. I want you to go in to the real data, and I want to set that equal to 5. Example, and you can do the same thing for the position dot image and set it equal to 5. So then you have this complex number that is basically 5 plus 5i. It can be very useful in other in several shaders that you want to write, because it combines these, puts them together so that people can read it easier and understand your thought process. Okay, so now that we've finally gotten over all the data types, we're going to go into actually writing the code in different constructs that we use. The first of is the if statement. So what an if statement does is it checks a condition that you give it, and then it executes some code, and then it exits this block. So this condition can be a lot of things. Generally, in a shader, it's going to be a comparison of values. So say you have a value declared A, you have some value, and you want to check, hey, you did some calculations on it, is it greater than 5? Okay, so if it's greater than 5, you want to say, maybe you want to take 5 away from it. So you say A equals A minus 5. So what this says is, okay, so if A is 5.5, it's a float, say, oh, this condition is true, I'm going to do this thing. So we're going to take 5.5, we're going to take 5 from it, so it's going to be 0.5, then we're going to put that into A. So then A equals 0.5. However, if A is less than 5, or equal to 5, so it's not greater than 5, it won't do this at all. It'll just completely skip it. Let's say you want to do two different things. If A is greater than 0.5, if A is greater than 5, you want to do this. But if it's not, you'll use something else. You can say, use the else statement. So what this says, this condition is not true. We're not going to do this. Instead, we're going to do this. We can say A equals A plus 5. But say, hey, maybe you don't want it to be just when this condition is not true. You want it to make sure that when A is less than 5. Because if this condition is not true, A could be equal to 5. So say you don't want to do this if A equals 5. So you give this an if statement. And if you only want one thing to be executed afterwards, you don't need to use the braces. But I tend to do so because it makes it easier to read, in my opinion. You could say A equals A plus 5. So if A is less than 5, we're going to add 5 to it. The great thing about if-else statements is that they're made so that you do one or the other. So if this is true, it's going to skip this else. If this is false, it's going to skip this block and check the else, the next if. And you can continue doing that. You can say another else if. And you can just keep going on forever if you would like to. Next, we're going to look at the while loop. While has a very similar structure to if. Is while this condition braces, we're going to execute something, then we're going to close braces. So again, the condition is going to be the same as in the if statement. The only difference between the if and the while statement is that it continues doing this execution as long as the condition is true. So if the program goes to this while loop and it's going to check this condition, if it's true, it's going to execute. After it executes, it's going to go check the condition again. If the condition is true again, it will execute again. And we'll just continue doing that until this condition becomes false. And then it's going to skip the block. and continue the rest of your code. One thing to keep in mind is make sure that your condition ends up being false, or you're going to get an infinite loop, which will just crash Blender. And it's not fun. So you have to be careful with the while loop. And then finally, we have this other one. It's called the for loop, and it has a slightly different syntax. So for this one, you generally have this integer called I, and when you get to the for loop, you say I equals, for example, 0. You semicolon, and you say I less than some value, let's say 20. Then you say I plus plus, and then you have execute like this. So first, what it goes here, it says I want to start this for loop with I being equal to 0. Then it wants to say I want to execute this so long as I is less than 20. And finally, it says after I execute, what do I do? You're gonna do this I plus plus, and you're gonna see this in basically every programmer's code. I plus plus is the same thing as I equals I plus 1, which is the same thing as I plus equals 1. So this one's probably the easiest to understand, first off, but you need to know these other forms so that you don't get confused. And this is a good point to show you that you can do this with basically any of these arithmetic uh, operators. So here you're saying I divide equals 1. So you're saying I equals I divided by 1. You could say times, and so on. It's just a shorthand, but if you feel more comfortable just saying I equals I divided by 2, go right ahead. It's not incorrect. It's just the other way is just make it less typing. And so again, this is going to be it's very similar to a while loop. In fact, you can actually use a while loop to do the same thing as a for loop, but for loops are just they're cleaner and crisper. The only difference between the for loop and the while loop is that a for loop has generally a limited number of executions, where a while loop you can keep executing until this condition is a certain condition stops being true. But again, if you're not careful, for example, if you were to say minus minus, which means that after you execute, you're going to take 1 away from I, that means that I is never going to be greater than 20. It's always going to be less than 20. So you're going to have an infinite loop, which is not good. Okay, I do believe that's all I want to talk about in the basics. We're finally going to get into the coding. Sorry if this is dragging on, but it's necessary to know all this. So I'm going to call this fractal. Even though it's not a true fractal, I still want to call it that. So when you start a shader, it's basically a program, but it's like a data type. It returns a shader or a closure. So you want to give it a type to be a type shader. It's like similar to the data types. This one specifically for when you're writing a shader. So for example, you don't have a type shader inside of C or anything. It's just only inside of OSL. So again, we have the type, and we have to give it a name. I'm going to call it fractal. Next, in OSL, you would give it an open parenthesis, and then close parenthesis down here. Inside of these parentheses, you're going to have your global variables. That is, the values that are going to be inputted and outputted of this node. So for this one, for example, I'm going to, first of all, you want the output closure color. I'm going to call it emission, because it's going to be an emission shader for the end. And you can set it equal to 0. Now, one thing to keep in mind is that when you're having multiple of these parameters, you actually use commas to separate them, but there's no comma after the last one, or it's not necessary. So we also need the points that we're shading in order to make this fractal. So we're going to say point, oops, sorry about that, point pos equals p. And we learned that p is the global variable for the position being shaded. I'm sorry, it's a comma, separate. Okay, so we have some rudimentary parameters right now. We'll add to it a little later as we need different ones. So this is where you actually write your code. So these are parameters. Here you actually can execute things. So this is where we're going to write our shader. So first off, we want to separate the x and the y from position. So what we're going to do, we're going to have type float to be our, we're going to call it real. And I'll explain why in a little bit. Real equals pos of 1. And the only reason I'm making, because the real should really be the x, but that it makes it kind of point towards the x, and I want it to point up, so that's why I made the real equal to the y, not the x. And then we're going to have float imaginary equals pos of x. So this looks very familiar, doesn't it? It's from our strut, but I figured for this code, a strut wasn't really necessary, so I decided not to add it to our code, just for simplicity's sake. So now we're making the x, the point, the value x of this point P to be an imaginary value and a real value. Of course, we really haven't set it to an imaginary value. We're just labeling it as an imaginary value. We're going to treat it as one later on. So to make a fractal, basically, you have this position called z because it's a complex value. It'll be your real plus your I. And basically what it says is z of n plus 1, that is the next z, or the next point, is equal to your z of n, or your current point, squared, plus your original z. But we're going to make, just to make it a little more exciting, we're going to make it zn. So what this is saying is the next point is equal to the current point squared plus your current point. So how do we do that? Well, to do complex math, I'm going to explain it down here. So you're going to have a value, you're going to have 5 plus 5j. So when you square this, you're saying 5 plus 5j multiplied by 5 plus 5j, where this asterisk is the multiply operator. This will not be multiplied, this would be an error. So you have to make sure to add that. And we'll explain the other operators right now. So you have your plus, which is obvious. You have your minus, which is just a little dash. And your division is just the slash. Just to be clear about that, so no one gets confused. So we have, this is a complex value. And if you guys remember from algebra, you have to do the FOIL. That is, first values multiplied together. So it's going to be 5 times 5 plus, then it's your outside values. Okay. 5 times 5j plus your inside values, 5j times 5 plus your last values, which is 5j times 5j. So we know that real and imaginary values are separated, so they can't actually add up together. So we have to keep them separated. So for example, we have 25. 5 times 5 is 25. Then 5 times 5j will be 25j. Next, you can have another 25j. And then you're going to have 25. Only thing is, when you multiply j times j, it equals -1. So really, two imaginaries multiplied by each other gets negative. And the reason I'm using j instead of I is because I study electrical engineering, and I is taken for current. Now don't ask me why current isn't C. C is capacitance. Don't ask me why. I don't know. It doesn't make much sense. That's how it is. So please, if I confuse you with writing J down, excuse me. It's force of habit. So what we're gonna do with this fractal is we're gonna use that thing, this little formula we learned, z equals zn plus squared plus zn. But we want to see how many times it takes for this next value to be greater than a certain threshold, which we're going to set it to. So to do that, what we're going to do, we're going to use a for loop. So if you remember from the for loop, we need an integer to increment. So I'm going to say int I up here. So up here I'm going to say I equals 0. Then we have to do I less than a certain value. I want to do this, check this 20 times. So we're going to go through that equation 20 times. And again, we're just going to do I plus plus. Generally, that's always how you want to do it. There are exceptions, however. So this can end up being, for example, I equals 5 plus 2. So instead of incrementing it, you're adding 2 instead of 1. But for now, we're just going to make it the standard. So there's two parts to this. There's a real part and an imaginary part. So if you remember from what we wrote down here, the real part is going to equal your real part times your real part minus your imaginary part times your imaginary part plus your real part. So we're going to add this value to the square of it. The imaginary, however, is quite different. Imaginary is simply your imaginary times your real plus your imaginary times your real, which means it's just 2 times your imaginary times your real. And then we're going to add the imaginary because we're adding this point to its square. And then finally, we don't want to go through 20 times for every single time, because there's going to be times where it's going to reach greater than 2 faster than others. But we want to find that out. So the way you do that is you have an if statement. You say, for example, we want to make sure that it's within the circle of 2. So we're going to say, to get a circle, it's going to be your value of x squared plus your y squared. And you're going to get a point somewhere on this circle. You'll have slightly different angles, but as long as you have that, it'll be consistent with a circle. So what we're going to say is, if, say, real times real plus your imaginary times your imaginary is greater than 2, break. So we're going to slow down here for a second. Realize that even though the square of an imaginary number is negative, here we're doing a positive. Because we're no longer treating it as imaginary, we're treating it as just the y value. And then this break. What the break does is it basically stops whatever loop it's inside of from continuing. So if we do this 5 times, and it says, hey, this is greater than 2, it's going to exit out of our for loop, which is very useful for this because we want to go up to 20, but we don't want to. If we don't have to go to 20, there's no reason to. So writing this in a while loop would be a little trickier. It could be done, but I just like the for loop better. So we have this statement. What are we going to do with it? Well, we're going to have this I value, right? It's going to get stopped somewhere. So we're going to have a value either from 0 to 20. So the way we're going to use this is, first we're going to have we're going to use our closure color, emission, and make that equal to our, if the emission closure, you don't have to worry about what this does behind the scenes. Just know that it makes a light. Let me spell it right correctly. So this is going to shoot out light according to a certain color. And then we're going to say, hey, the color we want is going to be, you have to multiply, because this just gives the intensity, right? We want to multiply it by some color to give it, not so it's not just white. So the color we're going to give it, I want to do it in HSV, because we'll get to play around with it a little bit more with HSV. So our hue is going to end up being, we want our own specific hue. So that means up here we have to give it a hue. So it's a color. So we want to say color hue, rather. I'm sorry, it's not a color. It's going to be a float. So I'm going to say equal to originally to 0. But then the user can set it so they can change the color if they want. Then we want the saturation. We're just going to set to 1. But this is where the code does something very interesting. We're going to make I divided by 20.0, so that depending on how many turns it takes to get for this loop to end, it's going to be the intensity of the color. So if it breaks, say, in five loops, then this is going to be a very dark color. But if it takes all 20 turns, it's going to be very intense color. Okay, so we've added that, and we are ready to test this. So we're going to, down here in our script, we're going to click fractal, and it did not, we have an error. Great, this is good. So it gives me the ability to show you the process I go through to debug. So first, we look and we see any obvious offenders. And if you were screaming at your computer saying, hey, this was the comma, good job. Because it is. You can't have any semicolons up here. Now we're going to test it again. Another error. So we're going to continue looking and see if we can spot this error. Okay, so here, it probably has to do with our emission here. We can check this by saying, changing this to an output color and getting rid of this emission. This is very important for you to learn how to debug, because you'll be doing it very often. But it's very annoying when you can't figure it out. But so you know that how the process goes, I'm going to continue recording. But I'm going to be looking at my notes right now to see what I might have done wrong. So we have this color, HSV,